My name is Peter Roth, and I'm a reviewer and associate editor for the Soundstage Network. And one of my favorite parts of being in the industry is that I get to spend time picking the brains of some of the smartest designers, whether they're amplifier designers or digital front-end designers or speaker designers. And so I've had the opportunity to spend some time getting to know a little bit more about the workings that go on underneath. And so what we wanted to do with this seminar was hopefully, bring our three experts, and I'll introduce them in a second, together, not to talk about their products, not to talk about their philosophies of sound, but rather to help the audience and myself better understand the thought processes that are confronted by a designer of electronics when thinking about, do I want to go with a tube-based circuit, or do I want to go with a solid-state circuit, or do I want to go with digital amplifier technology? And within each of those subsets, you have lots and lots of different approaches. You can have your single-ended triode, your output transformerless tube design. You can have solid-state with no feedback, solid-state with lots of feedback. You can have digital switching power supplies in an analog amplifier, or you can have digital amplification modules. So there's lots and lots of choices, and it's always interesting to me how much the devil is in the detail. And there is no right answer, and there's no inherently wrong answer, although there are lots of wrong results. And the great designers are the ones who know what they're working with, know the limitations of their approach, and know how to dial out the negatives while maximizing the positives in such a way that the end result is that people using their equipment can more quickly tap into the emotion of the music, which is what, as audiophiles, we're all trying to achieve. So let me briefly introduce everybody. At my far right, your left, is Jim White of Aesthetix, very well renowned for his tube phono stage and now a whole line of tube-based products from a digital front end through amplification. Steve McCormack, who's worn many hats over the last 30 years and has been well regarded for what he has achieved in the solid-state realm. And then sitting to my immediate right is Bruno Putzeys. Hopefully I got your last name close.
Recognizable.
Recognizable. So Bruno is from Belgium, and you may not know his name now, but I think that you will very soon. Bruno has worked at Philips, and where he developed some digital amplifier technology that was patented. And then he went on to work for Hypex, and Hypex makes a lot of digital modules that are in a lot of the products that are here at the show. And just now is starting his own consumer brand in Mola Mola, which utilizes some of the technology that has been utilized by others. And he continues to work for Grimm Audio, as well as Hypex. Grimm is another European-based manufacturer, and they do speakers and all kinds of other stuff and digital processing. But anyway, I mean, he wins the furthest traveled award for any of the seminars that I've done these past 3 years. So I want to thank all of them for being here. And what I wanted to do is I'm going to have this seminar broken down into 2 sessions. And we're just going to kind of go right to left and then right to left again. And the first portion will take about 5 minutes each, maybe not even that much. But what I wanted to do is there's so many acronyms. You've got FETs. Well, what is an FET device? Or what is the different kinds of acronyms that you see out there, and just what the feedback is, or local feedback and global feedback. And so I asked each of the 3 of them to think about the acronyms and the kind of major components that are in tube-based design, solid state, and then digital, to give us just a quick overview. And then we'll reset, and then Jim will take about 10 minutes and talk about the pluses and minuses of working with tube-based circuits, what the challenges are, what the benefits are of the designs, and same on down the line. And so we'll try to stay on schedule. Hopefully we can be even briefer on the acronym part, because I'd really like to hear from all three of them about the pluses and minuses. I know Bruno's got some images that he's going to share when he's talking about some of the digital switch and amplifier technology and the pitfalls and how it's done right and how it's done wrong. And one other thing I'd like to say is, while each of the three panelists are well regarded within these different camps, they all have worked in other camps. I mean, Bruno's first amplifier that he designed was a tube design, and Jim White worked at Theta Digital before forming Aesthetix. And obviously with his digital front end works with digital, and with his amplifier it's a hybrid design that has tube gain and then solid state output devices. So they're all fluent with each other, they all go beyond just these dedications. So my point is that they're not necessarily advocates for one, it's just that they're most familiar with one, and so they're not representing a whole industry. It's their own opinions, but done in an objective way as we can. So with that, I'll turn it over to Jim White of Aesthetix.
So I've been asked to define some various acronyms, and I wrote pages and pages of acronyms down that now have to fit in 5 minutes.
Well, just do your best.
You said keep it brief, so I think I'll start with something that's common amongst all three of us that I think could use some clarification, which is a single-ended and balanced operation.
Oh, that's a good one. We could spend the whole hour talking about that.
So basically with single-ended operation, you have a signal and you have a ground, and the signal is referenced to that ground, and any amplification that occurs is referenced to ground. If it's voltage amplification, the signal gets larger voltage. And single-ended circuits are simple. They require fewer components, whether it's solid state or tube. And they were essentially the first that were developed. Some of the negatives of single-ended design are they're susceptible to power supply instabilities or less than optimal conditions in your power supply. Anything that happens on the ground will be audible, and they also can be heavily influenced by noise and other external influences that get into the circuits. With balanced operation, or what we call differential, you have two signals that are, while one is going positive, the other is doing the exact same thing, negative. So they're just directly inverted of each other. And a differential circuit is only looking at those two signals and amplifying the difference between them. So as they get more different, the difference is being amplified. And the beauty of that is that if there's noise that's in common with those, like power supply hum or external noise coming in, that noise will be, if you have this signal going positive and the other signal going negative, that noise will actually be positive on both of them. And so it's only amplifying the difference, so that won't be amplified. So power supply hum is a perfect example of something that a differential circuit won't amplify. The negative of a differential circuit is you have two complete signal paths. So it's more complex, you have twice as many components, and it actually only works if the amplifying stages are the same. They are basically have the same characteristics. So in terms of gain and so forth. Going too much, huh? I can already tell.
No, it's a good discussion, but why don't you pick out one or two other kind of acronyms?
Yeah, let me get to tubes. So with tubes, which were the first amplifying devices developed, they're very simple in theory. Basically, you have something that's heated and is boiling off electrons, and some distance away, you have a very high voltage, and it's drawing electrons to it because of the high voltage. And that two-element device is called a diode, and that's what's used to turn AC into DC, essentially. There's other applications, but that's the primary. And the diode is also a solid-state device. There's analogies from tube to solid state. The next step in vacuum tube development was a triode. So they added a third element, and that third element is near the element that's boiling off the electrons. And by putting a negative voltage on it, you have a great deal of control over how many electrons are flowing to that positively charged. And this element that's near what's called the cathode, that's boiling off the electrons, is called a grid. And it allows the electrons to go through it because it's a spiral type wire. But its negative voltage has an electrostatic effect, so that the electrons, it has a great deal of control over the electrons. And by applying signal to that, you get amplification. And then from there, tubes developed into adding more elements into a tetrode and a pentode, which essentially just gave different kinds of effects on what the tubes can do. And they have various advantages and disadvantages in design. So with those tubes, the first and simplest amplifier was a single-ended triode, which is basically one triode. And you put a signal into the grid, and out of the plate, usually you'll have a transformer that's converting the high impedance into a low impedance to drive the speaker. And it's a very simple amplifier, very pure. It has limitations in it cannot deliver very much power, and very susceptible to power supply conditions, and the transformer is very large, and so it has limited bandwidth, but with a very efficient speaker you can get good purity, and that's what they're most known for, is a mid-range purity. From there, in the actual power amplifying stage, a development was made to use two tubes that are operating differential, or push-pull, so that you have, well, one signal is going one way, the other one's going the other way across a transformer. And that had lower distortion, higher power, it can cancel out even order harmonics. And then one of the developments that was actually invented in the 30s was popularized in the 60s with Dynaco, called ultralinear, which basically applied some portion of the signal to one of the other grids of a pentode, one of the other, called the screen grid. And that acted a little bit like negative feedback. And so it again lowered distortion and was a very popular circuit, and is still used today by many manufacturers.
Okay,
I'll stop there.
Sorry. And we'll come back and we'll talk more about the pluses and minuses of the approaches. So Steve?
I'm going to have to resist the temptation to elaborate on what he started about balanced technology. I get that question so much, it's tempting to go down that path, but that's not what we're here for today. So I've been asked to talk a little bit about the main acronyms associated with solid state. And really we boil that down to FETs, or field effect transistors, and bipolar or bipolar junction transistors. And then we sort of have to throw in operational amplifiers, or op-amps, into that. Although they're not devices themselves, they're circuits, that they're very handy building blocks that we use a lot in solid-state design. But the two primary devices are field effect transistors and bipolar transistors, and then there's many subsets within those fields. But broadly speaking, those are the two technologies that we make use of in their various forms. Field effect transistors are characterized by being very high impedance and are voltage controlled devices, and the bipolar transistors are typically current controlled devices, and that gives rise to a variety of pros and cons in their operation. And some people feel strongly one way or the other that one technology or another is better. I think it's been my experience that they both have their places, and both are extremely useful. And nowadays, of course, there's a fantastic number of devices and types to choose from. So each individual designer that's working in solid state gets to make their choices and base their circuit designs accordingly. The operational amplifier is a type of circuit that's characterized as having a differential input, the balanced business again, and a single output, and has extremely high open loop gain. But when we think about these things, usually we think about those little integrated circuits that we commonly see, the small DIP package, dual inline package, or that sort of thing, and that forms a useful building block for creating useful amplifier circuits. And again, many of those to choose from. You know, and there are popularity contests, as always, within audio about which one's the best and how to employ them. They're extremely useful devices, and I think the general consensus of feeling among audiophiles is that they are somewhat inferior to the best discrete circuits using discrete components. And although I would agree with that broadly speaking, it's also fair to say that with proper choice and proper care and feeding, op amps are capable of some very high performance levels and have found their way into a lot of components that we use. Shall we let Bruno go?
Yeah, let's let Bruno go.
Thanks. Actually, the Class D is fortunately not very littered with acronyms. First thing I'd like to point out is the thing which is not an acronym, which I've heard bandied about quite often, is digital amplifier, and so I'd like to get this out first. There is no such thing as digital amplifier. If you look at the archetypical Class D amplifier, you have a pair of switches which are being driven by a pulse width modulated signal, which in this archetypical drawing is created by a comparator fed on one end with a triangle wave, and on the other end with the audio signal. And what these switches then do is they switch the current, which is flowing through the output inductor, either to the positive rail or to the negative rail. And as you can see, these switches, they are dealing with current and voltage as a function of time. Now, these three quantities are physical quantities, and they are inherently analog. There's nothing digital in there. Even if the switches are, say, nominally used in a binary mode, either on or either off, the most of the distortion that you find in Class D amplifiers is generated in that very short time interval where the switchover actually happens, because that happens in a finite amount of time, and what happens during that period is dependent on the exact implementation of the circuit that you use to charge and discharge the gauge terminals of the MOSFETs. Well, here's an acronym. MOSFET is a particular kind of field effect transistor that's used for power applications, as in this output stage. Anyhow, so the gate charging circuit, the gate driver determines what the MOSFETs do during switchover. Also, the speaking current that's flowing at that moment will influence how fast the MOSFETs will actually switch, and so on. So these are really deeply analog behaviors that are fundamental to understanding the non-ideal behavior of a Class D power stage. Same thing with a power supply voltage. You're switching the output signal is actually switched hard between between the positive and the negative rail. Now, if there's going to be ripple on the power supply, well, if you don't watch out, that'll be part of your output signal. So it's really a 100% analog exercise, regardless of how much digital circuitry might be present in the control circuit. So I think.
So we should call them switching amplifiers, Class D switching amplifiers.
You may call them Class D amplifiers or switching amplifiers, but I personally consider the term digital amplifier a term of abuse. So let's put this here, and anyone who says digital amplifier in the coming hour gets to drop a quarter in it. What we do get in Class D amplifiers, as I said, not many acronyms, but you do get an inordinate amount of permutations of a few different items. Like there's, I've previously shown a simple output state with 2 switches. You can do it with 4 switches, and then you get the, let's say, you get the symmetrical variant of that. Again, there's no fundamental difference between this and the previous one. It's purely a matter of choice. Of technical choice, where you want to put the complexity in the power supply and the amplifier. It does change rather a lot if you go to if you then decide to drive these 4 switches independently, because then you can suddenly increase the amount of information that you can pack into the power stage with without increasing the switching frequency. So that's an interesting topology, unfortunately with quite a few pitfalls. You can increase that further to 4 phases, which is roughly what is done in the Mark Levinson 53. And then you can even go up as high as I did once, 8 phases. So that's one variable that can change, and which you can sort of glean from product literature, which of the variant is used. The output filter is another variable. If you, I've shown here just frequency response changes that you get if you load an output filter with different loads like loudspeakers or different resistances. And the question is, how did the designer decide to deal with that? That's another variable. How is the negative feedback loop arranged? Is it done before the output filter? Is it a mixed loop, or is it done after the output filter, which is actually the only correct solution? Let's see if this thing hangs up or not. No, it doesn't. There's a question: is this amplifier being driven, as I showed in the prototype, with a sawtooth or a triangle wave, or is the amplifier made to generate its own oscillation? And then you get these hybrid solutions like the bevy. I've just shown a picture here. If later on you have any questions about that, I can explain what they're doing.
Great. Okay, so now I know never to use digital again, and I will make sure I do remember to do that. So Jim, and in this next section, so when we're talking about the pros and cons, if we can touch a little bit on packaging and the user experience or the demands on the user, because one of the things that as a reviewer I'm always cognizant of is that I deal with, I get requests for what should I do, and or what should I listen to, and so one of my questions is, well, how are you going to use it? Where are you going to use it? Is it just going to be you, or is it going to be your whole family? How is what kind of music are you listening to? What size room? What SPL level do you like to listen to? There's so many variables that go into giving anybody advice, and they're all legitimate. I mean, somebody who wants their whole family to be able to simply use a system and leave it on all the time, and have connectivity so that it's got IP control or some kind of control system, that's legitimate. It's different than somebody who is only going to use a system for themselves. They only listen to vinyl. They come in, they turn on the system 30 minutes before they start using. They don't change any inputs. You know, they listen. It's a dedicated room. You know, there's just a panoply of ways you can use and interact with equipment, and the choices that the designers make, I think, has, you know, they have a vision of how their equipment's going to be used. So when talking about, you know, if the three of you would, just some of the, amongst the just performance aspects, just some of the kind of physical size limitations, user interoperability kind of componentry, or operational kind of considerations, how that kind of plays into it. What?
Yeah, I would say my approach is a global, holistic approach of making a product that will work universally. In talking about a power amplifier, I want it to work with 99.9% of the speakers that are in the field. I don't want someone to have to say, well, that amp is a great amp, but it won't drive my speakers. I want there to be a universal agreement amongst users, reviewers, etc., that this product is a universally good product and universally compatible. So that requires, in my opinion, it requires a decent amount of power and drive capability, current capability. So that kind of led me more in the direction of a larger, heavier power supply that is capable of delivering that those kinds of currents. And at the same time, balancing that power and compatibility with delicacy and mid-range purity that tubes bring. So that led me in the direction of a hybrid. And with the hybrid, we have a tube, vacuum tube triode, voltage gain stage, and then the output stage is solid state. And in the direction of power supply, I'm a big believer of choke input power supplies. And a choke input, I don't know if I should go into the choke thing, but
take a minute. I mean, that's the problem. I mean, you know, this kind of a format, we only have a couple minutes for everybody. We only have 50 minutes, or best case 50 minutes, because we've then lost some time. But you know, I want to go over everything as quickly as I can. But then, so talk quickly about chokes, but then maybe talk about how one of the things that was unique about the I/O. So Jim's first big product that created the acclaim and launched the company was the I/O phono stage, which came out in the early 90s when vinyl was viewed as a completely dying or dead on the vine format, and yet Jim had the great idea of making an all-tube phono stage, which didn't exist. So, I mean, while it might be a case study, I think it's a good example of what were the pros of that approach that hadn't been utilized by anybody, and what were the kind of the real challenges that had to be overcome.
Yeah, and I think that's an example of just seeing, not necessarily seeing in the market. I really designed that product for myself, and then it had a groundswell and developed into a company. But essentially, as Pete was saying, analog had become very small. Digital had really taken over, and I couldn't find a phono stage for my Koetsu cartridge. So that product was a 2-chassis, separate power supply, 24-tube high-gain phono stage. And it turned out there were other people who had low-output moving coils and no phono stage. So it grew from there. And so as part of that holistic design, for me, power supply is, I would say, half the battle. And I put tremendous effort into our power supplies and making them pure. And one of those approaches is a choke. A choke is basically an inductor. It's a coil of wire, usually around a ferrous core. And it is, if you put it after your rectification, after you've turned the AC into DC, your normal circuit will have a capacitor. And you charge a capacitor and you get filtered DC or stable DC with a capacitor. The capacitor, as it's only being charged as the waveform exceeds the DC voltage, and you get very sharp current spikes. With a choke, you have it creates a completely different type of circuit where you're actually charging through the entire AC waveform, and it's a very effective filter. It has better regulation, and you don't have those steep charging spikes. The steep charging spike, if you expand it out into an FFT, it looks like high frequency hash, and virtually every product we've ever made has chokes in at least the high voltage for tubes, and often in other areas. In the case of the Atlas, we actually have a choke input power supply for the high current output stage and a separate transformer just for the high current output stage, which is very uncommon. They're difficult to do. They have drawbacks. They're very heavy, very expensive, and they tend to buzz. So you have to deal with sort of manufacturing issues. But for me, the sonic benefits are worth it. But this is just trade-offs that maybe another designer would choose capacitor input and put more of that effort into other parts of the circuit that maybe have other benefits. So these are the trade-offs you're speaking of.
Okay. Steve?
Well, I certainly have to agree very strongly with the notion of designing my equipment to be universally compatible. I know some people have seen that, gee, if I make a kind of an enclosed system, you know, I do everything and they're all designed to work perfectly with each other, then I have more control. But I believe very strongly in making equipment that will work under any circumstance in anybody's system with whatever mix of equipment they happen to have. And oftentimes I get the question, what speakers do you use to design your amplifiers, or what other equipment do you use? And there's that concerns me a little bit. There's often a subtext there of, I want to know what I should buy. So I'm always quick to reassure those folks that I design equipment to work with their speakers and their associated electronics and their cables and whatnot, and that there's no, I haven't done anything in the design to limit its applicability in their systems. Now, as with what Jim was talking about also, especially with power amplifiers, I like to make things that are physically manageable by normal human beings. And even the largest amplifiers that I've made, although maybe not everybody would be able to pick it up and move it around, it's not absolutely gigantic. I like to keep things manageable. When you're designing with the sorts of linear amplifiers that we're working with, and the power supply is a very important consideration. When you want to make a high power system, that does have some implications for the size of the power transformer, the heat sinks that are involved, and those have consequences in terms of the physical size and weight of the piece that you're working on. So I do have various approaches that I use to keep those things manageable and not go completely overboard. I have chosen not to design Class A equipment because I feel I can get very good performance from the Class AB type bias systems that I like to use, and I can keep the heat sinks relatively manageably sized and not have to worry about a lot of excess heat constantly there, and still deliver very good performance as a for instance. So as Pete mentioned at the beginning here, there are endless choices and decisions that we as designers have to make, and there's a lot. Just it's hard to even think of how to talk about it, there are so many choices to make about, you know, the types of circuitry and the types of power supply and the types of chassis and circuit board materials and the different, you know, components that go into putting these things together. It just seems endless sometimes, and yet ultimately we manage to get a product to market.
Well, maybe you could just because I think that it's important, why don't you give us 2 minutes on the difference between Class A and Class AB circuits? Well,
the difference typically has to do with the fact that Class A, it refers to operating an output stage in a region where it never turns off, it never goes into saturation or cutoff. So the bias levels, the current that turns it on, is set high enough that the signal driving it will never cause it to go out of its operational range. The implication there is that the currents flowing through the output stage tend to be relatively high, and if the voltage applied to the stage is constant and high enough sufficient for whatever power that amplifier has, that gives rise to a substantial amount of heat constantly. And if you go to a different biasing scheme, what is often called Class AB, that means that the system the output stage will be driven into cutoff at some point, and you have what's referred to as crossover distortion. And some people feel very strongly that Class A is superior and that they can hear a lower distortion or a better sound or something like that. Class AB designs typically operate in Class A at lower signal levels and then switch into this Class B mode at higher drive levels. And my feeling is that properly designed Class AB stages sound excellent, and I don't hear the downside from that, and yet it is fair to say that Class A is still very popular among some people. And then designers have spent a lot of energy looking into ways to minimize the heat problems associated with Class A, and have come up with some very clever bias schemes that are variable sliding Class A bias, or they track the input signal and adjust the voltage drive to the output stage so that it's never more than just slightly higher than what is required to produce the necessary power at that point. And that's just to name a few. There have been some extremely clever schemes, some of which have worked rather well to keep the output stage effectively turned on and in what's called Class A, and yet avoid the classical downside of tremendous amount of heat and huge heat sinks and that sort of thing.
Great, thanks. So, coming to switching amplifiers, it's been, you know, one of the names that I think first people heard about was I think it's with the Bang & Olufsen Ice Power. Appeared as modules in a lot of different products, but Bruno's worked on, what was the first, the UCD Universal?
Yeah, Universal Class D.
Class D, which was, you invented at Philips, was that right? And then
I was still at Philips.
You were at Philips there, and then at Hypex you kind of brought that to more of a consumer. But why don't you tell us about this? You know, so from my perspective, it's really interesting. I'm so glad Bruno's here, because you have, you know, tubes have been with us since the birth of audio, and then solid state devices really appeared in a big way, I guess, at the end of the 60s, but really in the 70s, and then John Curl and some others were the first ones to be recognized to have overcome the limitations that were inherent in the early solid state devices, and then moved them to a point where they were recognized as being able to make fantastic sound as well. Class D is the latest kind of topology, and I know one designer told me that this is a speaker manufacturer at CES. He told me, you know, Class D is finally getting to a point of refinement where you know, it's sort of like digital sound was right at like 2000. You know, it took 15, 20 years until it got to a point where it was refined enough to really kind of break through. And he feels that now, and probably largely because of Bruno's work, that we're there, that the tipping point has been reached. But Bruno, in our correspondence, was quick to point out that switching amplifier technology can be done awfully wrong. And so, why don't you give us the differences between right and wrong, and how it's kind of come to the point that it's at now?
Well, the first thing to point out is that when you make the choice for Class D, you actually do so for only one reason. That is power efficiency, because you want to make something which is powerful and at the same time does not dissipate an awful amount of heat, and that will and to get to realize a very small form factor. Those are the reasons to go Class D. There is no other fundamental reason why you make that choice. However, once you've made it, the next question is, how am I going to make this thing sound good? And that is really the challenge. So, from a user perspective, as you asked in your first question, when as a user you have an amplifier on your hand which sounds good and which happens to be Class D, there are not really any drawbacks to it. The drawbacks squarely fall onto the shoulders of the designer, who will have had some serious challenges to work with. The first challenge which pops up is that compared to linear amplifiers, they are a very difficult starting point. A linear amplifier, for instance, if you run either a valve amplifier or a linear solid state amplifier without feedback, or with very little feedback, very often the amplifier actually flatters the sound. The distortion of linear amplifiers very often is more pleasant than no distortion at all, at least at first listen. With a Class D amplifier, that is not the case. So you have no other option at all but to apply gobs of negative feedback in order to achieve a very neutral, very clean sound. And that's it. And so every Class D amplifier that really achieves that point where people say, look, this can replace any linear amplifier. All of these Class D amplifiers will have been designed to a specification very clean, very neutral, very transparent, because you simply there is no sensible way in which you could turn them into a euphonic distortion machine. And so many of the precepts that are perfectly useful in the design of linear amplifiers become invalid in Class D amplifiers. And we have been through a very long and painful period, which started in the early 90s and which went on up till, well, certainly the mid of the previous decade, where people were foolishly trying to build zero feedback Class D amplifiers, sometimes driven using a digitally derived PWM signal, and the results were always very underwhelming. So with a Class D amplifier, the only possible stand that you can take as far as distortion is concerned is fight. Then other problems that you have to deal with is that this very fast switching is a great source of radio interference, and some amplifiers have been found in the wild that could turn off every radio and television set in the block by merely being turned on. And that is a very serious problem, because it's not only do surrounding radio receivers suffer, it's also the circuitry which is on that same amplifier board, which treats the incoming audio signal, that will suffer severe interference from the power stage. So then and even in the best cases, you're still forced to let go of things like star grounding and so on. You have to use solid copper ground planes and build a completely differential design. Anything else will fail essentially. And because it took so long to work out all of these details that you need to take care of, essentially very many experiments were done and even commercialized that seriously weren't any good. On average, when people say, "Oh, Class D is you rarely hear a good one." Yes, indeed, most Class D amplifiers are seriously challenges with these challenges unmet.
Why? Let me just ask a couple follow-up questions on that. Why was it that it seems like the first switching amplifiers that found most common usage were in subwoofers?
Well, essentially because we are much less sensitive to distortion at low frequencies, and also if you build an amplifier specifically for subwoofers, you can get by with lower switching frequencies. The whole problem simply becomes easier. So yes, practitioners of the technology have first had to pick the low-hanging fruit.
That makes sense. So you had mentioned, you showed one slide with the Devalier, which has gotten cover of Stereophile and lots of attention with that's its own hybrid approach, which my understanding is it's got a Class A amplifier at the signal or the gain stage, but at a very low level, and then it uses a switching amplifier for the current. Is that correct? I mean, it's just because it utilizes, they talk about Class A in solid state, and then the use of the Class D for the output stage. Maybe you just tell us quickly how that works, because maybe my hope is that it'll illuminate just a little bit more about kind of how the different topologies can be utilized together.
Well, I've drawn a quick block diagram. If there are any mistakes in the pluses and minuses, please bear with me, because I drew it whilst in the patio and just trying to knock up the diagram. What the Devalier, as it's properly pronounced, does is it amplifies the signal using an ordinary linear Class A amplifier, but one which is restricted in current. The output current of the Class A part is, or the standing current is so low that it will not deliver more than 1 watt. However, it will deliver the full output voltage. So it's not low level. Full output voltage is being reproduced by the Class A amplifier. The current flowing through the output of the Class A amplifier is then sensed, and there is a current regulated Class D amplifier, one which notably lacks an output inductor. So usually Class D amplifier has an output inductor. In the case of Devalier, the function of the output inductor, or the output capacitor, I'm sorry, scrap that. There is no output capacitor, so there's just the inductor. And so the Class A amplifier gets to absorb the ripple from the current ripple from the Class D stages, and that's why there are 4 of them in order to minimize that. And a current feedback loop will try to minimize the amount of current flowing through the Class A amplifier, so that the Class A amplifier is only calling the shots as far as voltage is concerned, but all the heavy lifting is then done by the Class D amplifier. And I should say, in fairness, that this is the first time that I've seen anyone do a hybrid solution with let's say part linear and part switching, which actually works. All previous attempts I've seen so far actually delivered worse performance than the best state-of-the-art Class D amplifiers at the time. I mean, the same problem is still bedeviling them, because the Devalier, again, still has roughly the same the same distortion performance like an Encore amplifier, and so they're still not way ahead. But in fairness, it's a very good sounding amplifier, and the performance is good.
Great. Okay. Well, we started 7 minutes late. We'll finish 7 minutes late because we were supposed to stop at I think 20 minutes after. But luckily, we don't have anything to break down, really. So we won't slow down the next seminar. I want to thank all of my panelists. I know that this is a fairly technical discussion, and one that is not necessarily the first one people would expect at a consumer event like this. But I think that it gives us all a better understanding that there are myriad choices, and that the great designers really understand the pluses and minuses of the choices that they make, so that they can extract the best possible performance out of the avenue that they're pursuing. Again, there's nothing right, nothing wrong. I thought it was interesting. Bruno said the only reason you go through the headache of a switching amplifier is because you want it to be small and not have any heat. So I know my mother-in-law has some Class D amplifiers tucked away in a cabinet because she needed it to be closed, so her interior decorator would approve. So that's a good example of the end user. But thank you so much to all three panelists. Thank you for coming. I hope you found it.
Thank you all for coming.